Chapter 11: Isotopes in Biochemistry. Some of the most spectacular advances in biochemistry have stemmed from the application of isotopes to the study of metabolic processes, a technique which gained impetus after the Second World War due to the rapidly increasing commercial availability of suitable isotopes. Compounds have been labeled or tagged by the incorporation of either stable or radioactive isotopes into their molecules, and then the subsequent fate of the molecule studied by tracing the movements of the labeled atoms. The major use of labeled compounds has been used to follow metabolic pathways. The appearance of the labeling in some isolated product of a metabolic sequence and the determination of its position in the molecule by suitable degradative procedures has afforded evidence of the existence of certain pathways. The feeding of labeled compounds and their incorporation in the animal body has demonstrated that bodily components are not necessarily inert simply because their concentration remains constant. The classical researchers of Schonheimer and Rittenberg have paved the way to the concept of dynamic equilibrium in the body tissue. Isotopes have also been used to determine the rates of reactions in living organisms where, despite the consistency of concentration of the bodily components, continual metabolic activity determined turnover occurs and can be measured by certain isotopic techniques. They are particularly valuable in the investigation of the kinetics of transport for molecules or ions across membranes. Selected aspects of the theoretical background to isotopic tracer work will now be considered stable isotopes. The atomic number of an atom, i.e. the number of protons in the nucleus, determines its chemical properties. The atomic number of an atom, i.e. the number of protons in the nucleus, determines its chemical properties. The atomic number of an atom, i.e. the number of protons in the nucleus, determines its chemical properties. Almost all non-elements exist as mixtures of atoms having two or more different atomic weights. Such atoms having identical atomic number but different atomic mass are termed isotopes of the element. Any subsample of the element consists of a mixture of isotopes, and the observed chemical atomic weight is therefore the average weight of the mixture of the different atoms and depends upon the abundance of each isotope in nature. Thus, chlorine has isotopes of mass 35 and 37 in such proportion that the determined atomic weight is almost 35.5, and the carbon consists of isotopes of mass 12 and 13 in the proportion of 99.3 to 0.7. Isotopes have almost identical chemical properties, yet may often be separated by differences in physical properties such as rates of diffusion and evaporation. In the case of deuterium, the isotope of hydrogen with mass 2, the situation is very favorable because it has a mass of 100% greater than hydrogen, and heavy water D2 or may actually be estimated by the difference in its density compared with ordinary water. If a suitable enrichment process of the suitable enrichment process of the proportion of one or more of the less abundant isotopes of an element can be increased, then a labeled element is produced and compounds containing the element will similarly be labeled. Alteration of the natural abundance ratio is achieved by the same physical techniques that are used by the separation of the isotopes, and of this fractional distillation electrolysis are the main methods used. The determination of the amount of stable isotopes present in an element necessitates use of the mass spectrometer for all cases determined excepting deuterium. The mass spectrometer produces a beam of rays of positively charged gaseous ions of homogeneous energy. With the application of electrostatic and magnetic fields, these ions are separated according to the mass, which determines their trajectory. An electrometer guided by a slit constitutes the measuring device. Application of a potential causes the mass spectra produced to traverse the slit, and each ion beam in turn enters the electrometer where the ionization current is measured. Information is thereby obtained as to the amount of the element of a particular mass present. It is on this type of determination that the use of stable isotopes in biochemistry depends. The abundance of the labeling isotope is compared with the normal abundance in the labeled starting material, and in the product of the reaction is measured. The degree of labeling a compound is always indicated by the atom percent excess. If an element normally contains Y atoms of a particular, say, heavy isotope, 100 atoms of the element, then there will be 100 minus atoms of the other isotope or isotopes, and the normal abundance is Y atom percent. Suppose that this abundance is increased to Z atom percent. In the process of the labeling, the difference between the enriched and normal abundance Z minus Y is termed the atom percent excess of the heavy isotope. Suppose that during the course of an experiment, the labeled material is diluted n times with the element accessing the normal abundance ratio. For every 100 atoms of labeled element, there will be a total of 100 atoms of the element. Of these atoms, Z atoms of the heavy isotope are derived of the enriched material, and Y in brackets and minus 1 close the brackets atoms of the heavy isotope are derived from the diluting material. The resulting element therefore contains Z plus Y open brackets and minus 1 close brackets atoms of heavy isotope in a total of 100 atoms, i.e. open brackets 7 plus Y close open brackets and minus 1 close brackets stroke divided by n atom percent, and the atom percent excess of the isotope is Z plus Y open brackets and minus 1 close brackets over n minus Y equals to Z minus Y over n. Since Z minus Y was the atom percent excess of the starting material, comparison of the atom percent excess of the starting and final material gives a measure of the dilution factor n. The use of stable isotopes helps like the base and considered radioactive ones wherever there is a choice between the two on the account of the easier methods of measurement and the greater sensitivity. In the case of nitrogen and oxygen, no suitable radioactive isotopes exist. The stable isotopes 15 and 18O are used. Stable isotopes possess the advantage that they are permanent, do not disintegrate with time, and furthermore produce no radiation effects on the tissue. Combination of both stable and radioactive isotopes permits the double labeling of a molecule, so that, for example, two different carbon atoms of a molecule may be labeled with stable 13C and radioactive 14C respectively. Radioactive isotopes for tracer studies may be prepared artificially from non-radioactive elements by means of either the cyclotron or the atomic pile. In this number, considerable quantities of radioactive isotopes have been made available for biochemical and medical research. Radioactive isotopes disintegrate spontaneously, giving rise to new elements and emitting radiation from particles or both. The disintegration may occur initially in one of the following ways. 1. Alpha particle emission. Alpha particles are helium nuclei, 2 helium or helium++, which are ejected from the nucleus of the atom. They are emitted only by radionuclides of high mass number, and in consequence are of relatively little biological interest. Beta-minus particle emission. These particles are emitted as a result of the nuclear transformation of a neutron into a proton. One nucleus into 1 0 proton plus 0 minus 1 electron. Positron beta plus emission. These accompany the conversion of a proton to a neutron. 1 proton to 1 0 neutron plus 1 0 1 electron. Positron emission is always associated with gamma ray photons, which arise from the annihilation reaction 0 1 electron plus 0 minus 1 electron into 2 Hb. For example, 11-6C, which with the half-life of 20.5 minutes is a positron emitter. Electron capture capture. An orbital electron is captured by the nucleus, resulting in a proton to neutron conversion. This transition is characterized by emission of X-rays, e.g. 55 ion has a weak K capture X-ray of 0.065 mega electrovolts. Isomeric transition. An unstable nucleus isomerizes without alteration in the proton of a neutron complement of the nucleus. The emission of gamma rays accompanies the change. In cases 1 to 4, there may be additionally the production of gamma rays with the energy of the emitted particle or X-ray where the energy of the emitted particle or X-ray does not account for the energy difference between the initial and final states. There is also the possibility that the emitted gamma rays may interact with the orbital electrons, resulting in the expulsion of homoenergetic electrons, a process known as internal conversion. Apart from the greater energy and hence shorter wavelengths, gamma rays do not differ fundamentally from X-rays, but from part of the electromagnetic spectrum, page 259, and possess strong penetrating powers. Their absorption by matter results in the secondary production of beta-minus particles, and so enables the detection by gas ionization difference devices primarily designed for the detection of beta-minus particles. Beta-minus particles carry a charge of 1 electron, 4.803 times 10 power minus 10 absolute electrostatic units, and the energies are recorded in electron volt units. An electron volt unit is defined as the kinetic energy gained by an electron when under the influence of a potential gradient of 1 volt. In practice, the mega electron volt 10 power 6 electron volts and kilo electron volts 10 power 3 electron volts are usually employed. The beta minus particles emitted by radionuclides are not generally homoenergetic but occur with a continuous distribution of energies from zero to another maximum electrons maximum characteristic of each isotope. The energy of beta minus particle determines its penetrating power and so influences the choice of assay system. Beta minus particles are classified as soft or hard emission depending on their energy. Table 11.1 recorded isotopes which have been widely used as biological traces. The Amax for determines emission half-life and whether or not they additionally emit gamma radiation. In the decay process, the elements undergo transmutation and the new element product of the process may be radioactive or non-radioactive. In the former case, the product which will undergo further decay until eventually a non-radioactive product is formed. For example, 14C is converted to 14N, 32P to 32S, and 40K to 40Ca and 40A. 14C, 14 carbon is converted to 14 nitrogen, 32 phosphorus is converted to 32 sulfur, and 40 calcium is converted to a mixture of 40 calcium and 40 argon. The conversion has a negligible effect on reactions being followed by the traces because of the radioactive isotope form, but a minor proportion of the number of non-radioactive atoms of the same element present in the labeled compound. A radioactive isotope disintegrates at a range which is a function only of the concentration of its nucleus, which cannot be altered in any way by chemical or physical means. As already seen in Chapter 5, the radioactive disintegration process is a first-order reaction, and the decay constant rate constant K is given by the expression K is equal to 2.303 over T log N0 over log N, where N0 is the number of the atoms of an element at a time t equals to 0, and the number of after a time t. The half-life period T half, or time required for the concentration of the decomposing element to reach half its original concentration, is expressed by the equation 5.6 T half is equal to 0.693 over K. Decay constants can be conveniently obtained by the use of semi-logarithmic graph paper, i.e. paper with one axis marked out proportionally to the logarithms of a number and the other marked out linearly. A straight line through points T and comma 2.1 and T n comma 2.2, where 2n and n are the number of atoms log axis at the times T1 and T2 gives a half-life period of T brackets close open brackets T2 minus T1 close the brackets directly. Units of definition: the Curie, the Ci, is the amount of radioactive isotope necessary to produce the same number of nuclear disintegrations as 1 gram of radium, namely 3.7 times 10 by 76 disintegrations per second, namely 3.7 times 10 by 7 disintegrations per second. This amount is far too great for normal biological use, and microcurie, and millicurie quantities 10 power minus 6 and 10 power minus 3 curies respectively find application as traces. Specific activity is the ratio of the radioactive atoms of an element, the total atoms of the same element present in the mixtures, e.g. 35S over 32, open the brackets 32S plus 35S as the dark brackets, and is usually expressed as curies, millicuries, or microcuries per gram or milligram of an element. Similar notation is used for compounds of the element, e.g. microcurie of the radioactive isotope, e.g. per milligram of compound, although a better notation is microcurie per millimole, which facilitates comparison with compounds of a different molecular weight. Radioactivity, when measured by the Geiger-Müller counter, is usually expressed as counts per minutes of a given weight of material. These counts are purely arbitrary units in biological work, and in biological work usually no effort is made to convert the count rates into millicuries. Commercially produced radioactive isotopes are supplied with a specific activity given in terms of microcurie or microcurie per milliliter of solution per microgram or gram of solid. Consequently, the term specific activity is applied to two different types of measurements. The count rate or material emitting soft beta minus particle is made at infinite thickness. Figure 11.1 is itself a measure of specific activity. Relative specific activity. Specific activities are frequently expressed relative to the specific activity of a reference compound, e.g. organic phosphates. Phosphates are relative to inorganic phosphate of a tissue or of the blood. They are then termed relative specific activities. turnover. This term is used to determine the renewal of a given substance by synthesis or by exchange or by entering of a labeled molecule into a tissue. Net synthesis can, of course, be studied by methods other than isotopic, but the tracer technique is particularly suited for demonstrating the incorporation of new molecules, which is being balanced by removal of molecules already present, i.e. whether there is no net increase in concentration, and classical analytical methods are of no avail. Beta emitters used in biological research, type of beta emission, beta minus emission, soft element, electrovolts max and microelectrovolts, other radiation emitted and half-life. Soft ion, 5526 ion, Emax nil, other radiation, Kalium, 2 times 94 years, tritium, 1 hydrogen, 0.018, other radiation emitted, not mentioned, to 12.4 years. Carbon 14.6 carbon 0.0 times 155. Other radiation emitted not mentioned 5568 years half-life. Sulfur 3516S 0.168. Other radiation emitted not mentioned half-life 87.1 days. Hard type of beta minus emission. Ion. Those are the television properties, the metallic alloys, the alloy properties of the mentioned radioactive material, which is telecommunication and mastering devices. Ion 5926 to 5926 ion 0.46, 0.27 gamma 45 times 1 days. Iodine, and those are the biochemical properties of the mentioned human beings in the master telecommunication and master devices, i.e. Bionic properties, biochemical, biological and mechanical properties, components of the vehicles used to transport the human beings into the laboratory stage. Iodine 13553 0 times 6.1 gamma 8.1 days. Potassium 1419 K 1 times 3.6 gamma, half-life 1.3 times 10.9 years. Potassium has half-life of 1.3 times 10.9 years. It has the highest half-life and the better type of emission. Sodium 2411 sodium maximum E volts 1.39 electrical volts, so a low voltage of less than 1.5 volts, and a half-life of 15 years. And so potassium half-life of 1.3 times 10 power 9 years. That means 1 billion years. And phosphorus has 3215 of an electron volt of 1.771 over 1.5 volts, but half-life of 14 times 3 days. And potassium 4219K. Also, an isotope of potassium has 36, that 3.6, 3 times 6, and 2.0 in gamma radiation. But this was mentioned, but it has a half-life of 12.5 years. Turnover time. The turnover time is the time interval required for the amount of a substance transferred into or out of a compartment or pool in the steady state to be numerically equal to the amount present in the compartment. Turnover rate. The turnover rate is defined as the absolute amount of a substance that is turned over in a unit time, i.e. the rate of appearance or disappearance of a substance A in the steady state, and has the dimensions of a mass times minus 1. This may be determined by the velocity of the reaction. The turnover rates are therefore expressed as grams or gram moles per unit time steady state. This applies to the situation where the rates of removal of the surfaces being studied from compartments are equaled by the rates of the replacement, so that the concentrations and amounts of the substances are constant during the period of observation. So that the concentrations and amounts of the substances are constant during the periods of observation. So that the concentrations and amounts of the substances are constant during the period of observation. In the steady state and with constant transfer rates for the unlabeled substance, the behavior of a tracer is independent of the reaction order, and the equations of describing the transfer of all have the form of equations characteristic for fast order reactions. A simplest demonstration of which of these is as follows. For a catenary system in which the tracer is not recycled, consider a one-compartment system of A to A through K into which an isotope is instantaneously introduced. Whereas the rate of disappearance of the isotope at any instant is proportional to the concentration of label A of A all, and at that instant is if first order kinetics are assumed.